Hello, and welcome to your instructions on how to create the plots for the Lab 1. Hopefully you've already watched the videos on what the test actually is and the basic kind of curves. And depending on the type of instruction you all got in the lecture, there's also the review of what are these curves and what data do they show, which is going to be important to you. But you're going to receive this file called Lab 1 data, and you'll see there's 5 sheets on here. And I'm going to create a sample plot for you based on these sheets. But I've created plots for you for aluminum, one of the aluminum samples, one of the steel samples, and one of the second aluminum sample. You have to create for aluminum 1 and steel 1 the plots. And you're only given pound force, so what was the load that was pulling on the sample, and the micro strain. So that's in microns. So that's already been multiplied times 10 to the minus, or times 10 to the 6. So really say this value of 52 here is 0.000052. So we want to quickly look at these plots, and I want to point out a few things that are on there. So initially, we're looking at the full stress strain diagram. So we have our strain in microns, our stress in PSI, and this is for a mild steel. And we can actually clearly see that perfectly plastic area that we expect in a mild steel showing up. And so it's easy to figure out at what stress this material yields at. It's going to be right along that plastic line. And in fact, we are going to need to know the yield stress, the ultimate stress, and then also what is the slope of this line here, E. Now, one of the easiest ways to figure that out is to actually do a zoomed in plot. And then as we look at this zoomed in plot, we can actually then draw a line across that plot, and when drawing that line, figure out what the slope is. So we can draw this line and figure out places that it crosses and simply do a rise over run from 2 data points. Now, one thing that's really important when you are figuring out your data is just due to initial constraints when we start the experiment, the plot may or may not, especially when we draw that what's the slope of E, it might not cross through 0, 0. And in fact, you might have to adjust your strain. I've put in a strain adjustment column in here, and if I actually have that strain adjustment, if I were to draw a line that I felt was linear and went through all of my points, we can actually see it doesn't cross through 0, 0. And so I created a way to move my plot left to right so that I could be sure that when I then drew my line that I felt was the most best linear fit, I'd be crossing through 0, 0, so that I could determine the modulus of elasticity of this material. So let's see what that looks like on a sample plot. So we're going to create this plot, but we'll start from a clean version. So again, coming in, all you have are the pounds and the microstrain. So we know we need to get the stress, but we also know we might need to adjust our plot left to right just based on sort of like tarring a scale, right? Maybe you just weren't quite at 0, 0 when the data started selecting or collecting, and that's not uncommon. So I'm going to go ahead and create 2 additional cells for us to work with. One, we need the area to figure out the stress. These are 1/2 inch diameter bars. So if we just take pi times our 0.5 squared, and then of course you'd have to divide by 4 because we're using diameter instead of radius. So we're going to have an area of 0.196 inches squared. And I also am going to go ahead and create an adjusted strain adjustment, a place where I could potentially put in an adjustment value for my strain. And right now I'm just going to set that at 0, so I'm not adjusting. And then I'm going to go ahead and make a new adjusted strain column, and I want to have a stress column. And so my adjusted strain will still be in microns, and my stress will be in PSI. And so to adjust the strain, I would just take the existing strain, and I may have to add or subtract basically a tarring to get us back to 0 value. So right now we're just going to add H2, and since I want to fill this down, I'll go ahead and put the $ in front of the 2 so I lock that row. So as I drag down, it doesn't change and it stays H2. For my stress, obviously that's just P over A. So the P is given to us in pounds force over in column B, and I'll divide that by the area that I calculated for a 1/2 inch diameter bar. And again, as I drag down, I want that to stay in row 1, so G1. So I'll put the $. You can put the $ in front of G as well, but since I'm just dragging down, I'm not changing columns. And now I can select both of those, grab the handle here, and drag down. And this has been taking data points every 1/2 a second. So if I drag all the way down, it was a 372-second test, and we can go back up. And so now we have our stress versus strain. And right now, the micro strain that was given and the adjusted strain are the exact same values because I haven't adjusted my strain in any way. And then I'll go ahead, I want to select columns D and E, and there's a great trick, Shift Control down arrow or Shift Command down arrow. But if I start at microns and hit Shift Control down arrow, it goes to the next blank. Go one column to the right, holding my Shift key, and now I have selected all of the data, and then I can insert a chart. And it's really important that we use a scatter chart. And when we use the scatter chart, we don't want to create any lines. We want to interpret the data. We do not want Excel interpreting our data. So do not add lines, just have your data points. And I do want to format this chart. I've made all the charts 7 inches wide and 4.5 inches tall, so you can have 2 charts on a page and it sort of puts the page in nicely. All right, so one critical thing that we're going to do, if you're writing a real engineering report, paper, some technical writing, you don't use Excel's titles up in the top. You're going to have a figure 1, figure 2 caption below. That's going to have the title of what this chart is and information about this chart. So we're going to delete that title. We, of course, though, are going to go into our chart design and add a chart element. You can often do this, especially on a PC, by right-clicking, but we're going to want to put in our axis title for our strain and give the units, not really units, but note that this is in microns. We want to add our vertical axes, and here we'll say that we're dealing with stress and give the units of PSI. And then the other thing you want to notice is our sample broke right here, but the machine was still collecting data. So we have like these negative load values down here, which are just sort of ridiculous because we didn't have negative load. And so we may have had a little bit as it was bouncing around these initial values here, but we don't worry about that because that's, again, the machine sort of setting itself, and we're fine when we hit these values. But just to have a clean chart, it'd be nice to get rid of this extra information. So select your chart so that you have the columns of data highlighted, and then we can just scroll down to the bottom, and then we can quickly see where we jump from 85,000 PSI down to 18 PSI. So just grab the corners of your data and drag it back up to where that's a bummer, to where we actually have real data on the chart. I want to make sure both sides match. It's not showing this data, but that's weirdness not to have it matching. Okay, so now basically this chart is relatively good to go. The only thing on here that is still missing and you might want to do is try to figure out what your max value is. So you could add a data label. It's hard to see, but that's about 100,800 PSI. Of course, you could easily found that information just by going to the bottom of your data and using the max command. And from the max command, it actually is basically 100,000, or you could say 100.8 KSI. All right, so we need to figure out our yield stress, and we need to figure out the slope of this line, and it's just really hard to see on this chart. So there's no reason not to do a second chart. And so we can look and say, all right, let's make sure we can see a little bit of this yield region. And so that's up here somewhere around, we add the data label, 55,000. So we can now reselect our data, scroll down, and we can definitely see here we've gone practice. Looks like it's just 55, 55, 55. Whoops. So I'm going to just grab one of those 55s. Oh, there's even more 55s here. Maybe I'll come back up to here. And I'm going to insert another chart. Again, doing a scatter plot. And wow, I can see I got a lot of the plastic range. That's probably more than I want. So I can go ahead and just drag these up a little bit. That's a little better. I could even go a little less. Maybe I'll go one more down. Okay, again, we get rid of the title. We need to add our chart elements. And I want to resize this by clicking on the format. So, whoops, just click the outside boundary, not the inside boundary. And I'm going to make it the same size, 4.5 by 7. Now, one of the things that I can immediately see if I wanted to come and just insert a shape, a drawing element, and let's say I wanted to draw a line, and I'm going to estimate, these all look incredibly linear right here. So let's start my line. I find it's hard to draw sometimes right on the chart. So I draw it off to the side, and then I just grab the grips and move it. So got a little steep there. This looks like I'm feeling a little better about this. It's running through these bottom points, right? It's running through these points. So I feel pretty good about this. I could also consider this, but now I feel like I'm getting a little high and I'm steepening out. So I'm pretty happy with somewhere about right here. The only problem is I see that I'm not hitting 0, 0, and that's problematic. And so I want to hit 0, 0, but that's now where we can say, okay, we just started a little early and got some extra strain values in there. So I don't have much strain. I might change this to negative 25. My whole plot shifts. I need to move my line over because my line didn't move, but as I move my line, I can now see that I'm pretty much crossing right through 0, 0, and I'm pretty happy with this line. To make the line easier to see, I can change its color. When we look at this, you'll also notice that we have this horizontal data on the bottom. That's going to happen a lot when you first put your sample in. There's some slipping, the machine's just getting the grip tights just right. You can ignore that data because that's not really telling us anything. All right, so now that we have our line and we're satisfied with how it crosses through the 0 axis, we actually need to pick our data points that we're going to work with. So as I look on this here, I actually really like this point because my line goes right through it. And right down here to the bottom, this point, because my line goes right through that. And then I have this linear, and some points are slightly above, slightly below, but those two are perfect crosses through. So I'm going to move the line slightly out of the way to make this easy. So here's how we do this. If I just click on the point, now see how I now have it selected. When I right click on it, I can add a data label, and it comes up, and it turns out this is 37,000. And so as we look, here's our 37,000, and it has a corresponding strain of 1205. So we can actually then come in and edit this text and go ahead and add in the 1205 microns. And I've had a lot of trouble editing on my particular Mac these values, so I'm just going to retype it PSI, and then we'll just delete that value back out. All right, so now I have this, and I've dragged it a little bit away from the plot, so actually the line connecting it. There we go. That's the one I liked. And so let's move that over here to the side. So I'm at 6175. So 6175 I can see has a strain of, we'll say 198.5. And so again, let's get in here and edit this text. So we said 198.5 is our microns, is our strain, and then it's at 61, basically 75 if we round up PSI. Again, no reason for more accuracy than that. And now I can move my line back down, again, showing how it goes right through those points and then through 0. And now we're just really interested in getting the rise over run because we're trying to find the slope of that line, because remember the slope of that line is our modulus of elasticity. So our rise over run, we would just have our, we'll put this in parentheses for Excel, 37012 minus 6175. And then we need to divide by the run. Now I'm going to put double parentheses. So first let's define what the run is. So that's our 1205 minus 198.5. But remember, that's in microns, so that's been multiplied by 10 to the 6. So we could either multiply the whole thing by 10 to the 6 when we get our answer, or I just multiply this by 1e to the negative 6, which is how we do that in Excel, to bring that back down to a strain value and not microstrain. And what I get back out is 30.6, and so what that tells me is E is equal to 30.6 KSI. And to complete this plot, then it'd be really great to label that on the plot because that's what it's all about. So we can go back to inserting shapes, insert a text box, put it right on our plot and say E is equal to 30.6 KSI. And I'm going to make that a little larger, and I'm not a big fan of having the border around it, so we'll go ahead and say no outline. All right, and so now we've created this plot and we know what our modulus of elasticity is. And we can identify basically right where we're yielding because it's elastic perfectly plastic. So we could also mark our yield stress or even just have a text box. And we only report these values to 1 decimal point, or we just do them as straight whole numbers. And so we know we're yielding basically at 55,000. So we could then say that our sigma yield, and let's go ahead and change our font to symbol all the way down. If we change to symbol, then sigma is just an S, and then we can change back to our Calibri. I'm not going to worry about going superscript or subscript right now. Is equal to, we said 55 KSI, and that's our approximate yield stress because we're in the mild steel, which has that perfectly plastic zone, and we can just see that we're at 55 up here. So that's how you're going to find E. Now, the one thing you also do have to figure out the yield stress, and if we were to say look at our aluminum sample, it's not as obvious. And so we need to do the 2% offset rule because as we look up here, we don't have this perfectly plastic section. So I'm going to take us over to aluminum 2. Now, on this particular plot, I've already found the yield stress, or the modular elasticity. I got that at about 9.7. Aluminum's usually around 10, 10.1, so we're within the range of acceptable error and the variations that you're going to have on any sample. That line should be running through there. And so you can see the points that I used, you can see the E value. You might have used slightly different points and got a slightly different E value, but within the range. Now, to get then where this is going to yield, we use what's called that 2% offset. So 0.2% offset rule, which 0.2% strain is actually just equal to 0.002, which is then also equal to 2,000 microns. Okay, and so what you want to do is you offset, so you have to offset your E slope line by 2,000 microns from wherever it crosses the strain axis. Now, I did a strain adjustment so that it would cross through 0, 0. But if you did not, and you're crossing, say, around 500 microns, you can't go just to 2,000 strain. You have to then go to 2,500 microns. But I can now basically take this line, I can copy it, and because I do cross at 0, 0, I can now just set this line right at the 2,000. So I'm now crossing at 2,000. Again, if we did have an error and our line was actually coming down at, say, 500, you would just offset 2,000 to the 500 mark. But we can go to 2,000, and then we actually pretty much hit a line or a node straight on. We're hitting this one. So if I add the data label, I can see that I am at 36, 37. So depending on how accurately you want to report that, we could say that our yield stress is going to be equal to 37 KSI. Or we could have said it's 36.7. And that's how you would find the yield stress on the aluminum bar. All right, you have to still now figure out aluminum 1 and steel 1, and then you can also copy the data onto a final sheet and plot all 5 plots on the same chart to really see how the data compares and how the behavior of the aluminum and the steel are similar and vary. Thanks for watching.